Okay, so let's continue from where we left last time. Just a second. Okay, so we were here, but before I proceed, let's go back and see what we were doing. So we were looking at these S matrix elements, which are basically these objects. So you have an in state here with m momenta and n momenta for the out state. Okay, and there are no other labels, as I said last time. For example, if you had a theory which had particles with electric charges, then you will have those electric charges also appearing in this list. But here all the particles are identical with the same mass and no electric charge, because I am looking at a real scalar field theory. Okay, so there are no other labels. And let's look at the algebra that we are doing, so that we can keep track of some factors, and if we make a mistake, we will hopefully catch it. So here in this step, we get a factor of root 2 omega k1 when we pull out, or when we get rid of the momentum k1 from the in state. Okay, so that's coming from normalization, and that k1 get replaced by a in dagger k1. Okay, and then of course there is a minus sign coming because of this thing which we did, and when I replace a out dagger and a in dagger in terms of this a dagger t or a dagger minus t, I get a factor of 1 over square root of z. So I get root 2 omega k1 over square root of z, okay, when I get rid of momentum k1. So at least these two factors are going to appear. Then here in this step, you see you got a time derivative of at dagger. Okay, and that brings in a factor of minus I. So that cancels this, but you get a factor of I. Let me show you. Now I have numbered the pages, so I know where it is. It's on page 20 or 21. Yeah, here. So here we had seen long back that if you, so this is the at dagger, okay, which is defined like this, and if you take the time derivative of this object in the above expression, so this is time derivative of at dagger. You see, it's exactly the same thing as above. Okay, it's identical expression. So I am taking time derivative of at dagger, and the result is minus I times this integral. Okay, so this is a source of an I in our calculation, and of course this minus I kills the minus sign we had there. So okay, let's go back. So one source of I is this one. Yeah, here. Okay, so what we say is, when I get rid of k1, I get root 2 omega k1, I get 1 over square root of z, and also, how do I move it? And also, when I convert this time derivative of at dagger in terms of the field phi, okay, then apart from other things, I bring a factor of minus I, okay, and that minus I, that minus sign gets killed to give you a plus I over square root of z. So you see at this stage here, what I have achieved is that k1 is gone. There is no reference to a in or a out. The only thing we have is the field phi. So this expression involves phi, okay, the field, and the overall factor is I over I times root 2 omega k1 over square root of z. Okay, and what we will see is that the same overall factor comes again when you get rid of the label K2, okay, which is here. Okay, so with this in mind, let's proceed. We have to keep track of many things now. Yeah. So at this stage, yeah. So where is it? Yeah. This is a shorthand notation for the out state. I have suppressed the labels, and here, so finally I got this overall factor which I have talked about times this integral with some function, with the function f, which we have seen several times, times this differential operator acting on this object, okay, this matrix element of phi. Okay, and then we started looking at only this matrix element of phi, okay, and we repeated similar steps. So you see again I'm getting rid of K2 and I have brought in a in dagger that comes with the square root of 2 omega K2, okay, and again this step which okay, so now I am looking at only this factor. This gives you 1 over square root of z, as I said before, because now you are converting a dagger out and a dagger in terms of a dagger of t and a dagger of minus t. So you get 1 over root z, and then that's where we are. Yeah, and that's where we are. So we haven't yet taken del naught of 80 dagger, so there is nothing to be said here. Okay, good. So we had eventually arrived at this expression minus I integral d cube x f k2 time ordered product of, some brackets are not very properly placed. Let me see. This phi x1. Okay. So I'll just look at my notes, that will be easier. So 1 over root z, this is fine. This is fine. T minus I. Okay, this is a square bracket. Okay, so this one is closing here, and then you have, okay, so this entire thing in the round brackets is time ordered. Okay, I should not have missed this. Now this is equal to, let's check, minus I d cube x time order product of fk2 del naught phi minus this okay, that is fine, and then you have minus I d cube x fk2 t del naught phi times phi x1. So this bracket is missing, so this is, these two operators are time ordered, minus del naught fk2 x, and then time order product of this, and here is the curly bracket closing. Okay, so this is fine. Now you see here you have in this term, second term, so these are just functions and derivatives, but the operator content is in here. So the time order product of phi of tx and phi of x1. Here also we have almost the same thing, time order product of del naught of phi tx phi of x1. Okay, now if I could interchange or take the del naught outside of t, then I would have time order product of phi times phi of x times phi of x1, and this will also have time order product of phi times phi x1, phi of x and times phi of x1. Okay, and these two will be the same factors. Now let us see whether we can indeed take this del naught outside of the time ordering operator. Okay. So here is, so I claim how should I do? Okay. So here, so I claim that time order product of phi x t and phi x prime, okay, by x prime I mean t prime and vector x prime, this, and if you take the time derivative with respect to t, this is same as time order product of del naught phi this is del over del t. Okay, and this is kind of obvious because because if you take this this time or look at the left hand side, you have time ordered product of these two operators. So let us say x the time t is smaller than the time t prime. So here this is phi of t prime x prime. Okay, so let us say t prime is smaller. Okay, then you have this sitting on the right and then phi xt sitting on the left. Okay, and if other way around, then you just interchange the order. Now when you take a time derivative with respect to t, that field phi is the time derivative is at that time, right? So del phi over del t is an object which is still defined at the time t. So the ordering doesn't get affected because of the time derivative, and this is what is the claim. Okay, but nevertheless I will do some algebra to show you, but it should be clear that this is a result which we should get. Okay, just because taking a time derivative of a function at which is defined at some time will not change, will give you another function which is again defined at the same time. But nevertheless, let me show this to you. So we have del over del t. What is this object? This is theta of t minus x 1 0. That's the step function. Okay, so only when t is greater than x1 0, this is 1, otherwise this vector is 0, times phi xt phi x, okay, x1 not x prime, I am writing x1. Okay, plus theta of x1 naught minus t phi x1 phi x t. Okay, that is the way you can write time order product of these two operators, and then you have the time derivative. So let us just do the differentiation. So time appears in this theta and in this phi. This one does not have t, so that is just going to sit out as a constant. So you have theta of t minus x1 naught times del over del t of phi xt times phi x1 plus, now I differentiate theta t minus x1 naught, and that gives you a delta function, delta of t minus x1 naught times this function. Okay, we will do the same thing to the second term here. Okay, and it gives theta of x1 naught minus t phi of x1, that's a constant, and then I take a time derivative on this one, del over del t phi of x t. Okay. Then I get minus delta of x1 naught minus t. Okay, so I differentiate this theta function, I get minus of this delta function. Okay. Okay, so this is what we get, and you see that these two terms, they just cancel. So this hits when t is equal to x1 naught. The same is here, t equal to x1 naught, otherwise this is 0. Okay, the delta function vanishes. So it makes phi of x t, and again, or let's say phi of x x1 naught, and phi of x1 naught. Similarly here, and these two cancel. Okay, they are identical. So you are left with this term, which is just time order product of del over del t phi x t. Okay, both of these terms have identical factor here, times phi x1. And you see they are time order because you have these theta function or unit step functions which tell which way it is ordered. Okay, so we have shown that indeed what we can argue simply is true by showing this algebra also. Okay, so we will use this, and I will take this and substitute it in here. Okay, so I will pull out the time derivative and put to the left, right, because that's what I have shown, that I can interchange the order of I can take the time derivative inside the time ordering operator or pull it outside, either way. So this gives you what? This gives you, so we'll continue from here. So this gives you yeah. So I will continue from that page. So you have minus id cube x, and then you have fk2 tx. Maybe I should go to my note, that will be better. fk2 tx, and you can meanwhile also write from your own notes. So del naught, so I am pulling out the derivative here, del naught time order product of phi xt phi x1, okay, minus del naught fk2 xt time order product of phi x t times phi x1. Okay, curly brackets, not yeah, should not put this. Okay, so that's good. Now with this I can okay, fk2, this is good. Okay, so let's go back and see what we have done. So here we were only manipulating this piece, this the thing in the curly brackets. Okay, now we should look at this entire thing also. So I have to take a time derivative of whatever I have written down here, okay, and integrate over x naught and put 1 over root z. Okay, and that is what gives you a dagger k2, a dagger out k2, phi minus phi times a in dagger k2. So maybe I should write down this entire thing so it's easier to read. So what I have shown now is that a out k2 okay, this thing is equal to 1 over root z limit t going, capital T going to infinity, minus T1 minus I epsilon to T1 minus I epsilon dx 0. So let's see, this is up to here. Okay, that's what I have written on that new sheet, and then I should take a time derivative of this object. So let's do that. Then I should take a time derivative of this expression here, this one. Okay, so I'm going to write that one out, minus I integral d cube x f k2 x t del naught of phi x t phi x1 minus del naught of f k2 x t time order product phi x t times phi x1. Okay, so I have just substituted everything, but remember this also, this expression also has to be put back into here in this one. Okay, but we'll come to that later. Okay, so what do we get then? So here you have a time derivative. This del naught is del over del t, right? So that it acts on this function f, because you have time dependence in here, and it acts on this phi or this entire object. Similarly, it acts on this and on this entire object. So if I do that, I will get the following: 1 over square root of z limit t going to infinity. Okay, I will just write dx naught, I will not write the limits explicitly. Okay, then you have d cube x from here, and then let's collect everything else. So this I minus I am going to pull out and write here minus I. Okay, everything, all the factors are taken care of, and then I get del naught acting on fk2, then del naught of, I'm just doing the differentiation, phi xt times phi x1. Okay, then second time the derivative acts on this one, so I get fk2 times del naught square, because del naught acting on del naught gives you del naught square of this operator Okay. Now let's look at the other term, second term, again del naught acts on this, so it gives you minus del naught square acting on Fk2 times time order product of phi xt, phi x1, and then you get minus del naught Fk2 and then the derivative acts on this time order product. Okay, so let's see the first term here and the last term here. Del naught of K2, del naught of K2, del naught of this time order product, and here del naught of the same time order product. They come with opposite signs, so these two cancel. Okay, so what are we left with is just correct, del naught square acting on this Fk2, and then you have del naught square acting on Fk2. Okay, and del naught square acting on, so you write down the expression of Fk2 that you already know. Okay, take the time derivative twice and substitute in here, and you will get the following. You will get the following result. Fk2 xt, remember Fk2 is an exponential function, the time dependence is exponential, so you will get Fk2 back when you differentiate twice here. So that's why I am able to take it out, and you have del naught square here. Okay, and this one will give you minus gradient square plus mp square. Okay, just doing the differentiation will give you this thing, and then you have the time order product of okay, so this is what we get, and this is what is sometimes written as box plus mp square. Okay, this operator box is just del naught square minus gradient square. Okay, very nice. And good. So now I will take this and substitute in this. Where is it? Yeah, in this expression. Okay, so that I obtain what this factor is. Okay, so I am going to write down now this factor. So what we have is now, maybe I should write down this gives P1 to Pn phi x1 K2 to Km, and this is in state, that is out state. Okay, remember, if you are getting lost in the algebra, just remember that we are one after one removing these momenta from the in state and replacing by phi's. Okay, that's what we are doing, and this is what we had got. This factor we had gotten when we had done it for the first time. Okay, when I took this thing, this inner product, and when I first time replaced K1, I had gotten this expression. Okay, apart from some integrals and some functions and derivative operators, I was left with the matrix element involving one label less in the in state and had replaced that by phi. So I am writing result for that factor now. So this now I have shown that this is equal to 2 omega k2 square root I over root z. Okay, remember, because I am going to remove this k2, I am going to get this factor root 2 omega k2, and also remember I get I over root z every time I repeat these steps as I had talked earlier. So I am going to get this times limit t going to infinity, okay, and instead of using x here, the variable I was writing as x, I will just, because this is dummy, I will just write it as x2, okay. So d4 x2, then you have f k2 x2 t, then we have box 2, okay, the box is with respect to the label x2, so I am writing box 2 with the subscript 2, this, and then we have out p1 to pn time order product of phi x2 phi x1. Okay, I will write that in the next line. Okay, times box 2 plus mp square, okay, where mp is the physical mass, okay. So I have now from k3 to km, I have gotten rid of k1 and k2, and instead of those I have got two fields here which are time order product, okay, and then these operators. So now I will take this and put back into this expression here, expression A, okay, and that is what I am going to do now. So S, now we are almost there, at least as far as making our first important result explicit is concerned. I have the following. So that's the S matrix element. I have shown that this is equal to, so I am substituting back into this expression, okay. So I get I over root z when I get phi x1, phi of x1, and times root 2 omega k1, and then I get again I over root z and root 2 omega k2 when I have phi x2. So I will take care of those. So I have I over square root of z into I over square root of z twice, because I have these two factors. Then I have 2 omega k subscript 1, then again root 2 omega k2, I don't know why I said subscript 1, and then I have integral d4 x1 d4 x2 f k1 of x1 f k2 of x2 times you have box 1 plus mp square, box 2 plus mp square. Okay, remember we got these operators every time, each time, and these act on this this matrix element. Okay. Okay, now you can imagine what will happen if we were to get rid of K3, K4 up to Km. Okay, each time I do that, I will bring in a factor of I over square root of Z, corresponding to omega K. Let's say next one is K3, so root 2 omega K3. Then you will have a new integral d4x3. Then you will have f of x3, fk3x3. Then you will have a corresponding differential operator here, box 3 plus mp square, this thing, and you are going to get time order product of phi x1, phi x2 and phi x3, and then one label less. And then again you repeat until you hit the vacuum. So at the end you will have only vacuum left. Okay, and then you will have a bunch of, all these things will be correspondingly repeated. So I am going to write down that result. So if you continue removing these labels k one by one, you are going to get eventually I over square root of z. How many such factors? M such factors, because there are M labels in the in state. So each time you get this, so you have a factor of M. Then you will get 2 omega k 1 square root of 2 omega k1 square root of 2 omega 2 and so forth. So you will get this. Let me write here product of I, or maybe just write that way. K1 times Km. Okay, so this is also a factor that you are going to get. Then okay, times fk1 x1 fk2 x2 fkm xm, okay, times these differential operators okay, and then eventually you have time order product of phi x1, phi x2, phi xm, okay, and you have vacuum here. We have gotten rid of all the the entire instate, and we have replaced it by the vacuum. Okay. Now, if we should do the same thing to the out state, okay,